Assalamu alaikum everyone. This is lecture 7 on Control System Engineering 1. We are discussing chapter 2, modeling the frequency domain. In the last few topics, actually, we have seen how to derive the transfer function from the electrical system. Then we have seen how to derive the transfer function for translational mechanical system, then the rotational mechanical system, and finally, the mechanical system with gear, how to derive the transfer function of those have been discussed. Today, we're going to, in the first topic, we will try to merge the electrical and the mechanical system and try to find out the corresponding transfer function. For that, we will start with the DC motor. So maybe fixed field DC motor. So we'll have maybe the more diagram, something like this. So we have the armature resistance, then we have inductance in the armature, then we have okay, so this is the motor, then we have the shaft, so the rotor shaft. Okay, so this may be a torque TMT, and your angle, corresponding angle, or angular movement, or angular velocity. So start with the theta, then we'll also try to see how if the angular velocity comes, how to deal with that. Okay, so this is your armature resistance RA, this is your inductor LA, and the applied voltage in the armature, that is EAT. Then your armature current IAT, and also the field. Don't forget about the field. So field, we are considering fixed field. Fixed field means either using a permanent magnet or an electromagnet, but supplied with separate voltage source so that it doesn't affect the changing of the flux. So simply we call it fixed field. Yeah, so for this system, actually we have to figure out the transfer function. The transfer function is basically from output of this device is theta ms, and the input, that electrical input that we are applying is EAS. So this is our required transfer function G of S for this electromechanical system, and we have to figure it out. Okay, so for figuring out the transfer function for this electromechanical system, let us write the corresponding equation. So we have the single loop, so we can apply the KVL in the single loop, so that will give us RA. We are directly writing in the Laplace domain, RA IAS plus SLA IAS plus VBS. We haven't said what is VB, the voltage across the motor, the back EMF that we call. So that is actually our VBT here. Okay, so summation of all the voltages should be equal to the supply voltage, or EAS. So for finding the transfer function, we know that in one side you have to have all the input, in the other side you have to have the output. The input is already in the other side, so in this side somehow we have to bring all the inputs. So how can you do that? So first thing is VB. So we know from electrical machine, I think you already know that EB, the thing that you know is EB equal to 5ZN by 16 into P by A. Something like this, you already know, generator action of the motor. So that can be actually simplified using K, because only the two parameters that can change is phi and n. Okay, so again, n can be converted to omega. Okay, so omega is actually radian, omega equal to radian per second. So you can write it radian per revolution into revolution per second. So that will give you radian per revolution is twice pi. And then if your n is in terms of your revolution per minute, then just simply n, otherwise n by 60. So you can put n here. So we assume that this n is a revolution per second. So this is how you can relate it. Bottom line is with another change of the coefficient, maybe we can say that k1 phi omega equal to your E. Okay, so and also phi is a constant, so we can say that this can be considered as a constant. So kb EB equal to kb phi. But we are talking about the dynamics here. So basically, according to this diagram of the motor, so you can write that it is actually nothing but your VBT. So VBT will be equal to kb omega t. Okay, so just according to this diagram, we just change the name of this one and this one, and also put time variables here because we are talking about the transient of the dynamic nature. Okay, so similarly that, but we are interested about theta, not omega. So we can write kb d phi m. You can also put m here, t by dt equal to your vbt. Okay, so we can easily take the Laplace transformation of it. And Laplace transformation will give us VBS equal to KB. Different derivative is nothing. Initial condition is 0, so derivative is nothing but just multiplied with S theta S theta ms. Okay, so theta ms. Okay, so sorry about it. So it will be theta as well. Okay. Okay, now easily we can replace the VB from this equation here with theta m. But in the other side as well, somehow IA is the parameter that has to be converted into theta m. So how to do that? So for that, another motor equation that we already know. So this is one we are going to use. And the other, for other one, we know that our tau, armature uh, torque is basically proportional to K phi IA from the motor. We know that. And now phi is also constant, so we can assume that tau equal to basically KT IA. Okay, so these are all constants. So according to this circuit that we are discussing, basically this is nothing but your Tm. So Tm and also the dynamics. So in the Laplace domain, it will be something like this: Kt IAS. Okay, so what we have in this equation is IA. So IA has to be replaced by Tm. So IA has will be basically tau by Kt. So now we put these two into this equation, then let's see what it becomes. So before applying this, we can actually make it we take common of the IA. So RA plus SLA into IAS plus BBS equal to EAS. So now replace the VB by the corresponding parameter KBS theta ms equal to EAS. Similarly, now your IA can be replaced by RA plus SLA into torque tau m S by KT. Okay, so here now, actually, we don't know yet what is the relation between the tau and your torque, because in one side we already have the input, but other side the tau m should be replaced by theta. So we have to figure out that relationship as well. So let's say this is our equation. So this was 2, this was 3 now. So say this is 4. So we have to come back to 4 again. So how we can relate? So mechanical load can be assumed as it has inertia as well as friction. From the nature of the motor, we know that it has a friction with the bearing as well as it has a yaw friction. So the bottom line is one equivalent uh, inertia as well as one friction parameter, equivalent friction parameter may be there in the load. So we'll have something like this: Jm, inertia, motor inertia, and dm, the motor friction or viscous friction. So that will be actually related to our tm, sorry, tau mt, that is torque, as well as your angular theta mt. Okay, so now we know actually how to write the equation for this one in the Laplace domain. So Jms square plus dms into theta ms should be equal to tau ms. Okay, so from this one, you can easily replace the value of tau into this equation. So what it will become now is Ra plus SLA, then your J ms square plus dms theta ms, okay, divided by your kt, plus you have kb as theta ms equal to your eas. Okay, so now one thing we can do is we can take a common of s from here to make it similar to this one. Okay, and also we have to assume that in general the value of the resistance is way high compared to the inductor. Okay, so based on this assumption, actually we can avoid this parameter. We can assume that it's very, very small. So majority of the contribution of the effect is given by Ra. So basically, so what you can write Ra by Kt. So this kind of simplifying assumptions we always have to take to make things easier. So what you have is Jms plus dm and s theta ms plus kb s theta ms equal to eas. Okay, so if we want, we can take further, we can take common of s theta ms. So basically, Ra by kt jms plus dm plus kb. Okay, so s theta ms equal to eas. So now we have almost arrived to our corresponding transfer function. So basically, theta ms by eas will be 1 by s into that parameter. So that is Ra by kt, jms plus dm, then we have plus kb. Okay, so we don't want to keep any coefficient of s in the denominator in general. So let us multiply, simplify, and then what we are going to get here is basically uh, I'm just skipping one or two lines, so you try to read by yourself. Otherwise, the class lengths are becoming more than 1 hour and 5 minutes, so which is very lengthy. So that is why you just at times I will keep one or two lines for you. You do it by yourself. 18 by RAJM and S plus 1 by JM dm plus 18 kb by RA. Okay, so this is our final transfer function. Even though there are a lot of parameters, seems a bit difficult to understand, but this is essentially nothing but a simplified version of it is nothing but some coefficient k by s into s plus alpha. Okay, so s plus. Okay, so this is your k, and this is your. So a simple two-pole system is your DC motor, fixed field, or actually separately excited, or permanent magnet DC motor as well. So this is your corresponding transfer function. So we actually have to use this equation again. Somewhere I think this equation is, we somehow have to use this equation as well after simplification. So let us try to figure out what are the problems here we are going to face. So basically, if you want to find out the transfer function, what you have to find is what is Jn, what is Dn. This is what you have to figure out. Then you also have to figure out what is Kt by Ra, as well as if they cannot be separated. Okay, so Kt by Ra and then also Kb. So somehow we have to find out a way to figure out these parameters, numerical values of this, then we actually can go for solving the problem. So let us do some more derivation. How can we actually figure out these parameters? So to figure out these parameters for a motor, how actually Jm and Dm is calculated. So for the motor is having most likely can have a rotor, sorry, the gear attached to it. Then finally the load side, you will have the load inertia as well as the friction that is happening. Okay, so there is two things basically. One is motor inertia, armature friction, as well as your number of teeth N1, N2. Then you have load inertia and load uh, friction. So this is your motor. So how to figure out Jm and Dm. So basically we can take this parameter to the primary side or to the motor side. So you know the destination divided by the source teeth ratio square should be there. So we can easily calculate what should be your Jm. Jm should be equal to Ja plus N1 by N2 square into JL. Similarly, Dm can be calculated as Da plus N1 by N2 whole square into DL. So calculating these two are relatively simpler. Now, let us try to figure out how we can calculate those parameters, those two, that is Kt by Ra and Kb. So for calculating those, we have to assume that equation, that is Ra by Kt. We already assumed that Ra is greater than Ln. So that is giving us this equation. Then you have T tau m s plus Kb s theta ms equal to Ea. Okay, so we are not replacing the tau by omega, just we want to find out the relation between the speed and the torque, so basically motor characteristics. So if we take the inverse Laplace transformation of this equation, then that will give us R A by, sorry, this is KT, so R A by KT tau MT plus KD, and this is nothing but your speed, isn't it? So d phi by dt is nothing but omega. So this is omega MT, then it is your EAT. Now, since this is a DC motor, after the transient is vanished at steady state, these will be actually constant parameters. So time dependence will be over after transient period. So basically what we can write here is RA by KT, then you have tau M plus KB omega M equal to E. Now, if we rearrange this one, if we just let's say multiply everything by KTRA, Tm equal to KT KB by RA omega M minus H should be there since we have taken it to the other side plus KT by RA E. So this is nothing but actually y equal to minus mx plus c. So we are trying to find this is your y, this is your x. So we are actually having an equation that will give us a curve like this. This is your motor torque speed characteristic. So motor torque speed characteristic, you already know, I think, from your electrical machine one. So we'll have a characteristic like this, Pauling characteristic. So this is it can be drawn for different values of EA. So for different values of EA, say this one is for EA1, this one is for EA2, this one is for EA3. So a series of curves is actually coming based on different values of EA. And also we can have this thing here that is called no speed torque or tau stall torque. This is tau m. This is actually omega m, and this is actually called no load speed. So omega no load. If there is no load, what will be the speed? That is your omega no load. So these two, at this point, whenever we are calculating tau stall, actually we are considering omega equal to 0. Similarly, whenever we are calculating omega no load, actually what we are doing is we are assuming that this one is 0. So based on this thing, from this equation, you can easily find out what is the value of tau stall. So for tau stall, this parameter will be vanished. So what will be left is tau stall equal to KT by RA into EA. But we are actually interested about whether you forget or not, KT by RA, what is the value of that. So tau stall by EA is actually, we can get the value of KT by RA. Similarly, if we try to calculate the omega no load, then torque has to be equal to 0. And based on that, actually we can figure out that omega no load is omega no load equal to EA by KB. So, but we are actually interested about KB. So omega no load is known, also EA is known. So we can say that KB is EA by omega no load. Okay, so a lot of derivation, a lot of things we have covered here. Now, actually, what we want to do is we want to figure out, we want to solve one practical problem. So let us try to use all the formulas that we have derived here to figure out the transfer function of a practical system. So say this is your example 2.23. Yes, so this is what is being given. Resistance already assume that inductor is smaller. So we have this scenario here. E A T I A T. Then we have R A, and also using a gear. Load is also connected. Load is also connected. Okay, so this is the case. So the parameters that is given here is N1 equal to 100, N2 equal to 1000. Then you have JL is given. JL is 700 kilogram meter square. And then you have DL is given as well. That is 800. Okay, so Newton meter second per radian. So Newton meter second per radian. Okay, also the parameter JA is given. So JA, armature inertia, is 5 kg meter square. Then you have armature friction, that is 2 Newton second per radian. Okay, so anything we are missing? No, I think these are all. So the curve is also given. So your motor characteristic curve is given. So you have something like this. This is 500. This is 50, and this is drawn for E equal to 100. So T stall and omega no load already known in the curve. So what we have to figure out is theta L S by ES. So only the difference is we calculated theta L, which is in this side. So this is your theta L S, but we have to calculate it here, theta S. So we'll deal with that one later. First of all, whatever we know, the formula, let's try to check what is known to us and what we have to calculate. So theta ms by you have EAS equal to basically formula says KT by RA JM S S plus 1 by JM DM plus KT KB by RA. Okay, so what do we have to find out? We have to find out what is the value of JM, DM, KT by RA, and KB. Okay, so let us start with the value Jm. So Jm is basically Ja plus J is 5 plus a destination tip, that is 100 N1 divided by the source, that is N2, okay, square into 700. Basically 1 by 10, so 100. So basically 5 plus 7, so basically 12. Similarly, what is your DM? DM is basically now similarly you have 2 plus same ratio, 100 by 1000 and 1 by n2 whole square into 8. So basically it will be 10. So two parameters already figured out. Now what we have to figure out is KT by RA as well as your KT by RA and KB. So for KT by RA, we already know this is your T stall. So T stall is this, and this is your omega no load. Okay. So the formula is KT by RA equal to tau stall. Tau stall. Sometimes I say T, sometimes tau, but it's always better to say tau. So I'm sorry for that. Maybe it is due to the age. Okay, so tau stall is 500 and EA is 100. So you can easily find KT by RA will be approximately 5, as well as what about the KB? KB is EA by omega no load. Omega no load. So EA is 100, omega no load is 50, so it's 2. So we can now directly put all the values here. So KT by RA is 5, JN is 12, so it will be 5 by 12. Then you have S plus 1 by 12 into dN is 10 plus KT by RA is 5 and KB is 2. So basically what we are going to get is 5 by 12. Then you have S plus 1, 20 divided by 12. So what we are getting is 5 by 12 is basically 0.417, and then you have S plus 1.667. So this is theta ms by ES. But we actually have to find out theta L. So theta m has to be replaced by theta L. So theta ms by theta ls, which is basically theta 1 by theta 2, is inversely proportional to n2 by n1. Okay, so what we are going to get here is 100 divided by 1000 divided by 100. Or we can say that theta ams can be replaced by 10 theta ls. So if you put it here, then what you are going to get is 10 theta ls by EAS equal to 0.417 divided by S into S plus 1.667. Okay, so now take the 10 on the outside. So this is your corresponding transfer function that we are looking for. Theta ls by EAS equal to 0.0417 divided by S into S plus 1.667. Okay, so that's all. How to deal with the practical scenario with the circuit. If the circuit is given, how to figure out the corresponding transfer function. Okay, so with the physical parameters, electromechanical circuits or electromechanical systems, if you say. So another version of it is actually given in skill assessment exercise 2.1. So skill assessment exercise 2.11. Here, only the difference is there is 2 gear being used. Okay, so in between the motor and the load. So I think 2 gear should not be a big problem. You just have to use it to transfer. So if you have 2 gear, then you have to transform twice. So if it is N1 by N2, then N2, and so then if you want to take the impedances to the other side. So this is JA and DA is already there. This is your JL. This is your DL. So you have to take twice, and destination is N1 and N3. So basically JN you have to calculate in this way. JA is already there in the other side. So you'll have N1 by N2. Then you have N3 by N4 whole square JL. Similarly, dm will be also the same thing, dA plus n1 by n2 into n3 by n4 whole square dA. So this is 2 gear, so it is not a big problem, I think. And the other thing that has been given is instead of given the curve, they have given the equation of the load and the speed, torque and your angular velocity. So basically, they have given this equation, tail m equal to minus 8 omega m is 200. So idea is very simple. You take omega m equal to 0 and then you calculate tau stop, which is very easily can be found as 2. And then take omega m equal to 0 and then find omega no load, which will be basically 200 divided by 8. 2 different. So rest of the problem is same. So I think you can do it by yourself. So you don't want to spend too much time to just increase the size of the class. Okay, so next topic, the last topic of this chapter is basically article 2.9, that is electrical circuit analogs. So article 2.9, electrical circuit analogs. Okay, so what is analog? We can say electrical circuit analog. So the definition is electrical circuit analog is an electrical circuit, basically, that is analogous to a system from another discipline. That is called electrical circuit analog. So system is in other domains, say mechanical system, and we are trying to represent that mechanical system by electrical circuit. So that is what is called electrical circuit analog. Okay, so let us start with, so if we try to, and for that actually in the electrical circuit, we know that we have mesh equation. Okay, so mesh equation, or we have nodal equation. But in mechanical domain, we have only one thing, that is equation of motion. So if you compare the mesh equation with equation of the motion, then it is called series analog. And if you compare nodal equation with your equation of motion, then it is called parallel analog. Okay, so parallel analog. Okay, so these are the definition, what is analog and how we compare the equation, and based on that equation, actually system for other discipline is being presented by electrical circuits. So that is why it is called electrical circuit analog. So let us start with this thing. So say we have a RLC electrical and RLC mechanical system, I mean the similar systems. So a mechanical system with the spring and the damper associated mass. You have force Ft. You have the displacement with the reference is your xt. So this is your mechanical system. And how can I represent the mechanical system? So far, what we have learned is ms square plus fvs plus k into x s equal to fs. Okay, so similarly, for the mesh analysis, we have to go for the loop or the mesh. And in the electrical one, we have something like this, say, inductor, resistor, then capacitor. Okay, so this is your, say, ET. So current is IT. This is your L, R, and then you have C. So now, if we try to write the equation for this one, what will be our equation? So impedance Ls plus R plus 1 by CS IS should be equal to ES. But actually, you cannot compare these two equations because they are not similar. But if you divide this thing, if you divide this thing by S and multiply S here, then what you can find is MS plus AV plus K by S. And S axis is nothing but velocity, isn't it? So linear displacement and linear velocity Vs equal to Fs. Now, actually, you can compare these two equations. So if you compare these two equations, they are almost identical. So what you can do, you can represent the mass M, mass by which parameter? Just by comparing this and this. So we can see that mass can be represented by inductor, and the values are actually proportional. So you can say M Henrys. Okay. So then FV can be represented by resistor. So FV is actually friction or viscous damper. So whatever you prefer. So FV, that thing will be represented by a resistor. And FV, they are also linear FV ohms. Okay. Now finally we have K as well as C. They are inversely proportional. So spin K that will be represented by a capacitor, and its magnitude will be 1 by K farads. Okay. Similarly, what about the force? The force Ft can be represented by voltage source, no, it will be Ft. And then your current, that is velocity, V small vt, can be represented by mesh current or loop current, mesh current. Okay, so it can be represented as VT local. So now this system, mechanical system, mass spring damper system, we want to represent it by this according to the equation that possess. So according to the equation, how can you write it? So this is nothing but current, this is nothing but voltage, this is your inductor, this is resistor, this is capacitor. So we can simply write, we can draw the electrical diagram. Okay, so with the inductor, with the resistor, with the capacitor, and the corresponding values now will be writing the mechanical values like Ft. This is your Vt. This is your M. This is your Fv, and this is 1 by K. Okay, so now mechanical system is entirely represented by electrical notations. So this is what is called electrical circuit analog mechanical system, and this is since we are using the mesh analysis, mesh equations, so it is called series analog. So in one of the problems previously, we have actually derived the equation something like this, a complicated one, M1 S square plus FV1 plus FV3S plus K1 plus K2. That is your X1S minus common was actually FV3S plus K2. X2S equal to F. So this is what we already previously derived. So now to apply the electrical analog, we actually have to change this parameter with voltage. So we actually have to divide it by S and multiply with S. Velocity, sorry, not voltage. Similarly, this one is divided by S and multiplied by S. So what we are going to get after conversion is M1S plus FV1 plus FV3 plus K1 plus K2 by S. Then you have V1S. What is V1? Loop current, similar to the loop current. Okay, so minus. Then you have V3 plus K2 by S. And you have V2S. So second equation, I am just writing directly. So common is actually minus FV3 plus K2 by S, V1S plus M2, M2S plus FV2 plus FV3 plus K2 plus K3 by S. In the next two, there is no, V2. V2S equal to 0. Now, these two equations we have to represent by electrical equipment. So, as you can see, there is two velocities, V1 and V2. So, definitely there will be two loops. So, some component will be common in between the loop, and those components are nothing but these ones are common. So, we can write those commons. Okay, so V is represented by resistor and K is represented by a capacitor. So this is value is FV3 and 1 by K2. Okay, so some component is specific to the loop 1 and some component is specific to the loop 2. So the components that are specific to the loop 1 is this one, and this one. So basically one inductor, one resistor, and one capacitor. And also you have a voltage source in the first loop. So you have the voltage source as well. So this is your Fs. So you can represent in the time domain as well. It's only the magnitudes. So this is your current direction. So the velocity direction will be V1T. Okay, so the components that are only dedicated to the loop 2 is M2. Then I think FV2 and K3. So again, three components, inductor, then you have a resistor, and then you have a capacitor. Okay, so this is your loop 2. So this will be your V2. Okay. So magnitude wise, this is proportional M1, then FV1, then 1 by K1. Similarly, M2, then you have FV2, 1 by K3. So this is a mechanical system represented in electrical components. So actually what is our intention is, it's difficult for us to deal with the mechanical system, but electrical components are actually easier for us to handle. So that is why these analogs help us to convert the system from other domain to convert it to the system of our known domain. As a result, it becomes easier to handle. So this was your series analog. But for your parallel analog, so what we have is same mechanical system, that is with spring, damping, and as well as mass. But this time we'll be using the nodal analysis to parallel things. So current, then you have node here, node voltage E. Then you have capacitor, then you have a resistor, then you have a inductor. Okay, so this is your I. This is your node voltage ET. Okay, capacitor, resistor, inductor. So if you try to write this equation, the equation is same as before. So you can write ms plus fv plus k by s, and then you have vs equal to fs. Now, if we try to write the equation for the electrical network, so we're going to help taking the help of the admittance. So what we are going to get is admittance is cs plus 1 by r conductance, 1 by ls is your susceptance. So basically that is a summation of all the admittances will give you multiplication with the node voltage will give you the current, source current. Okay. Now it is possible to compare this. Now what you can say is now mass M can be represented by capacitor, and they're proportional. So basically M farads. Okay, so then you have friction damping, kV. We represented by H. It is always remaining same. This over guide is not changing nature. So is it proportional? No, it is inversely proportional. Okay, so 1 by kV, 1 by kV ohms. Okay, then what about spring? The spring, so it is actually AV. Okay, so spring K is represented by inductor, and also the relationship is inverse. So 1 by K will have this. Now, what about the force? Force is now actually F2 is analogous to your source current. Okay, so Ft, and your velocity Vt. Vt will now be represented by in the node voltage. So node voltage. Okay, so Vt. Okay, so same equation that we have used previously. We are going to take help of the same equation, and then we have to check how can we deal with it. So basically, this to same equation. So for applying on this equation, let us erase the thing in the downwards. Okay, so it's somehow. Okay, somehow the erasing thing is not working, so I'm not sure whether I can take a copy of this thing. No, this individually can take a copy as well. Okay, so okay, let us just compare this thing here. So with the same equation, or if it is difficult, we can actually, even though we have to repeat, let me write it again so it will be easier for you to deal with it. So the final equation that we actually obtained was M. Okay, now it works. So basically M1 S plus FV1 plus FV3 plus K1 plus K2 by S V1 is minus V3 plus K2S V2S equal to Fs. Okay, so this was your equation 1, and equation 2 was minus V3 plus K2 by S V1S plus M2 S plus AV2 plus AV3 plus K2 plus K3 by S. V2 is equal to 0. Now we have these two equations. So using this parallel analog, how can we represent it? So now V1 and V2 velocities are actually represents the node voltage. So basically it says that there should be two nodes. So one is V1T, the other one is say V2T. So there is some component common in between these two nodes. So these are the common things. So one resistor and one inductor will be there. This K is now representing inductor. So one resistor and then one inductor will be there. So this is 1 by V3 and this is 1 by K2. Okay, so some parameters are dedicated for only node 1. So the ones that are dedicated to the node 1 is basically M1, then FV1 and K1, as well as the current source will also be there. So three components will be there, one capacitor, one resistor, and one inductor, as well as the current source. So current source is your FT. Then you have this components. This is simply your M1. Then this is your 1 by FV1 and this is your 1 by K1. Okay. In the other side, what are common? Common is M2 and then FV2 as well as K3. So another three component will be in the other side as well. That is one capacitor, one resistor, one inductor. Okay, so what are their values? This is N2, this is your 1 by FV2, and this is your 1 by K3. So this is how the same network can be represented using the series analog or using the parallel analog. So this was the last topic. Actually, there is another topic, 2.1. 1110. So nonlinear system. So that is not part of this course. So we'll be actually avoiding going into that topic. Rather, we'll start chapter 4. So chapter 4 on the next week. Next week. Okay. Okay, see you in the next class, inshallah.